Yeah, if one thing became clear today, then and it became clear over and over again, then it's that understanding the effects of chemicals is like a huge jigsaw puzzle with hundreds or maybe thousands of pieces. Not only, as we heard, do we look at an increasing number of substances, we also look at the combination of substances in our environment and subsequently also in our human body. And to make matters even more complicated, not every human being reacts to the chemicals in the same way. So in this jigsaw puzzle, we face numerous possible interactions and combinations. Understanding them better is at the center of work of our next speaker. Please give a very warm round of applause to the head of Department of Health at Karlstad University, Sweden, Professor Carl Gustav Bornehack.
Hear me?
Yes. I can hear
you. Thank you very much for inviting me to this meeting, a very important meeting. And today I'm going to talk about how HBM values can be used for the very urgent and also very complicated issue of risk assessment of mixtures that was introduced here. I will upload my I hope you can see my slide.
Yes.
So this issue is then based on both suspicions, but I also would say real data and evidence that even if the single compounds are found below guideline values, there might be a mixture effect because we are, as have been said here several times, exposed for a combination of very, very many substances simultaneously, and I will show more about that in a second. And as also been said here before, part of the HBM story is about going into these mixtures and look. Just for a short background, what we are doing, usually doing for regulatory purposes is to compare the human exposure with reference doses which come from experimental evidence. And this is a very old way to do it, and it has been very successful in history to get rid of dangerous exposure, no doubt about that. And another thing here is that because of that, nearly all risk assessment of chemicals have been based on a single compound approach. The problem that have been told earlier as well is that we are never, ever exposed to one chemical at a time. We are always exposed to very, very complicated combinations of very many different chemicals. This is data from our study in Sweden, the SELMA study, where we have data from far more than 2,000 pregnant women. And this is just a picture of 54 different compounds in urine and serum. And don't go into details here, but just look at the red column to the right, where we show data on in how many samples in percent that were detected over the level of detection. So you can see that for all these compounds, 75% of these compounds were found in every mother in this cohort study. So there is no doubt about that we are exposed for this. And we quite recently finalized a European study in Horizon 2020, the EDC mixed risk study. And that was focused on to come up with better tools for doing risk assessment of chemical mixtures. And the overall idea of that was to combine epidemiological data, human data, with experimental systems. And then by this interaction and outcomes from this interaction, provide better risk assessment of society, of mixture exposures. And I mean, this was a huge project, but one of the outputs from it was that we developed different approaches for doing risk assessment of mixtures. And one of them is the so-called the SMAC approach, which is stand for sufficient similarity. And I just going to show here, before I come back to the HBM values, how this was built up and what kind of output we did get from it. So this is a stepwise procedure going from, I would talk about the first step in this procedure. So we start in step number 1 with human data, cohort data, where we try to find mixtures in prenatal exposure. We call them bad actors. The bad actors constitute the mixtures that are associated to different kind of health effects. If we can do that, we can produce those mixtures. We can establish reference mixtures in tubes, so to say, and then in step number 3, we send over these mixtures that are both human relevant but also health relevant from a population point of view. We send over them to the experimentalists, and they do studies with the overall aim to come up with dose response, if that is impossible. If we can do this, then we can ask 2 questions. If we find mixtures, if we could find mixtures that were relevant, and if we could find dose response relationship, we can follow the same principle as we have used for single compounds, but in this time for mixtures. And then one question is, of course, if we find a mixture that is of relevance, then we are interested how many people are exposed for that mixture, because this is one of the problems, that we are differently exposed. And this is a term then called sufficient similarity. This is not a very complicated story, but it's a little bit math behind this. But the first question is then, how many are exposed for a sufficient similar mixture? The second question, 4B, is to use kind of a regulatory ratio for the mixture and asking how many out of this that have a sufficient similar mixture in their body, how many of those are exposed to extreme mixing proportions, mainly if this is a value above 1, then these people are under risk. And this is also similar to the single compound approach, but now we talk about mixtures. So in the EPI part, we are looking on the exposure early in pregnancy. We in this case, we have used 20 compounds, and we try to find by different techniques, by mixtures of compounds that are associated to health outcomes. And in this case, we are dealing with 3 domains, so to say. It's about metabolism and growth, which is birth weight. We talk about sexual development, which we have measured as anogenital distance in baby boys. And we talk about neurodevelopment, which in this case is language delay at the age of 30 months. So this is the first step in the story. The second step is to produce these mixtures that should be sent over to the experimentalist. And that is based on if we in the EPI, in the first step, can identify the bad actors, then we know the mixing proportions of these bad actors from the Selma mothers. So we have data from nearly 2,000 mothers for these compounds, and we know quite exactly what a typical mixture proportion for these is. And these values and this information have then been used for establishing mixtures. And then we can test them across concentrations And you can see here that 1x is then standing for a typical SELMA mother exposure. And then we can go up to 1,000 times of that, and we can even go lower than that. Then in the experimental settings, we have, in this case, then 3 different mixtures. One mixture for growth, one mixture for sexual development, and one mixture for neurodevelopment. And they have then been established in the EPI part. And then we have used different models, and here you see examples. The mixture G have been evaluated in the experimental systems in zebrafish, where we are looking for metabolic rate. In mixture S, we are doing the same thing. We are measuring mouse AGD. And in the third one, we have used the Xenopus with it and thyroid disrupting evaluation of these. And the point here is to find to examine if we can find dose-response relationship. Otherwise, it doesn't work. So, going a little bit more into details, this is for mixture S. In the first part here to the left, this is the bad actors we did find among the 20 compounds, and the mixture of these 4 compounds was associated to a shorter anogenital distance in baby boys. In the middle of the picture, you see by the use of the geometric mean in serum and urine levels, we could find the mixing proportions. And then to the right in the figure, we composed a reference mixture to be used in the experimental system. And this mixture S then was used in a mice model in Greece. And here you can see the dose-response relationship that was established. On the x-axis here, you can see the doses, the concentration of mixture S to these. This was to pregnant mouses, and we measured the AGD divided by birth weight, body weight for their pups. And you can see that when the exposure increased, the AGD distance decreased, which was expected and was exactly what we did see in the human data as well. Then we established a benchmark dose, which was, in this case, a 5% decline in the AGD distance. And that then correspond to a benchmark dose of 0.49 in this scale, and this was a logarithmic scale. So, but the point here is that at a dose of almost roughly double typical SELMA dose of mixture S, we had a 5% reduction in AGD. So then we have done the first 3 steps. We identified bad actors, we composed the mixture, and we tested it, and we did find the dose response. So then we go into this sufficient similarity. And this, I won't go into detail to this, but the question here is easy. We are just asking how many of the mothers in the SELMA study had the same, a sufficient similar mix in their bodies of these compounds. And we could find out with this, by the use of the benchmark dose, we established what we call a similarity region. And we could find that 83% of the SELMA women had a sufficient similar mixing proportions to mixture S in their bodies. Okay, the second question was, can we, by the use of this similar mixture risk index, which is a way to say that if this value is above 1, then these mothers are under risk to get a boy with a shorter anogenital distance than median value. And we, in these analyses, could then see that around roughly 15% of the SELMA mothers had a concentration extreme. They had a value for SMRI above 1. And that was among those 83%. So among the total population, we could find that 13% had an SMRI above 1, which is then expressed as a risk. For comparison, and for this mixture S, we looked at, if you evaluate these compounds with the typical strategy, namely based on a compound by compound, then we could find that 1.6% of these mothers were under risk. If we use the additivity model and estimate the so-called hazard index, we could find that 3% of these mothers were under risk. And by this whole mixture approach that I've showed you here, we could find that around 13% were under risk. So by using this whole mixture approach, we could almost had a 10 times higher risk than if we used the single compound approach, which is currently the strategy we are using. The details of these calculations you can find in a publication. I won't go into details of that. I mentioned for you that we used different animal models, and here is some results from the sexual development here in the middle I just talked about. It was about anogenital distance in baby boys. We used anogenital distance for mice, and you can see that 83% in the population had a sufficient similar mixture in their bodies, and 13% of the total number in Selma were at risk based on this. If we go for metabolism and growth, we used birth weight in the Selma study, and then we used a zebrafish model and looked for metabolic rate. And here you can see that quite a lot had a sufficient similar mixture in their body, but the SMRI value above 1 was quite low. So this doesn't look to be a risk, high risk here. And for neurodevelopment,
Professor Bornehag, sorry, it's Katrin Prüfig here in Berlin. Sorry for interrupting you. We have to be fairly strict with the timing here today. So I just wanted to let you know that maybe 1 minute left if you like to come to a conclusion.
I am ready for that. So for the language delay, we use these, for the neurodevelopment, we use the experimental model on zeta spike with the thyroids here. And we could see that 52% of the mothers from this was had an SMRI of 1. So then we have used this SMAC approach. But the one question here of importance is then, okay, this was made in Sweden. Then we can ask the question, how relevant is this on a European scale? And this is the final conclusion here, that testing the generalizability of the findings we have in EDC mix risk would be possible to do in HBM4EU values or IPChem. And the point is that for this testing of the generalizability, we don't need any health data. We just need HBM value, the values in different countries, the concentrations or the exposure in different countries, which is a very important question because we don't know if the exposure on a mixture level is the same in Sweden and other countries. Thank you very much.